Thank you. Just a little note, anyone who starts to yawn, I'll be asking random questions, so be warned. All right, this is the first, my first talk in the 2011 Harry Butler Wild West series. And it's about a group of extinct marine reptile called the Ichthyosaurs. It's quite tricky to pronounce. It's, the name itself is derived from Greek. Ichthys means fish, and saurus lizard, so the fish lizard. Let's see if I can remember. Just to give you an idea when these marine reptiles existed. If we go back, now this is where we are now, the Holocene. If we go back in time, this is the age of the dinosaurs, and go all the way back to the Devonian period. That's when the first amphibians ventured onto land or developed into amphibians from fish-like ancestors. And the amphibians, they flourished throughout the Carboniferous period. But at the end of the Carboniferous period, the climate became much drier and colder, and we actually had a major ice age around the Carboniferous Permian boundary. And during this period, reptiles evolved from amphibians. And reptiles, that gave them a big advantage. Since reptiles, they can lay their eggs on land, whereas amphibians, they're far more dependent on water. And if the climate becomes drier, that obviously gives reptiles a big advantage. So the reptiles, we had land-living reptiles, but around 245 million years ago, one type of reptiles, they returned to the sea. Much like whales, for example, who evolved from a land-living mammal. Just for those of you who have no idea what kind of animal an ichthyosaur is, you could argue they look pretty much like a dolphin, very dolphin-like in the body morphology, especially the later forms, the more advanced forms. The only an obvious difference, apart from them being reptiles, and dolphins obviously are mammals, is that in a dolphin and whale, the tail is horizontal, whereas the ichthyosaur had a vertical tail. Another interesting feature is that they had absolutely enormous eyes. Some of these, one particular species of ichthyosaur, they had the largest eyes relative to the body size of any vertebrate animal. The eyes itself would have a diameter up to 25 centimeters. That indicates that they obviously could hunt when the light levels were very low in the ocean. These were strictly marine animals, so they didn't occur in rivers, only in salt water. Another interesting feature is they evolved a tail, no, tail is back here, a dorsal fin that's not supported by any of the skeletal elements here. This is a skeleton of an ichthyosaur. I would presume this one is probably found either in England and Germany, where they found many very well preserved ichthyosaurs. You can see here the impression of a dorsal fin and a tail fin here, and you can see that it's the lower lobe that is supported by the vertebral column. The vertebrae, the backbones in later ichthyosaurs, they were very short relative to their diameter. That's a very characteristic feature of the vertebrae. Another interesting aspect is their forelimbs. They're very much developed into a paddle over millions of years. I mean, I'm going to show you another image that we can see actually how that whole process took place. Here's another ichthyosaur. Anyone see anything peculiar with this one? Yes, exactly. It's a very sad, it's a very sad story. You can see here's a little baby coming out of the mother Ichthyosaurs, and all these little bones, they are remains of unborn Ichthyosaur babies. So obviously she died while she was giving birth, and it also shows that these reptiles, they didn't lay egg like a turtle. They would just be too difficult for them to crawl up on land. They were too specialized, too well adapted to a life in the oceans. Some of these ichthyosaurs, they became absolutely huge. This one is Shani Soros, and they found one a few years ago, or maybe 10-15 years ago in British Columbia, and they estimate the length of that individual to 21 meters. So these are by far the biggest marine reptiles of all time. And here's another smaller one of a different species. As adults, they lost much of all of their dentition, so they basically only had teeth as juvenile, and that only applies to these really gigantic forms. There's one place in Nevada where they found a large number of these Kronosaurus individuals, and one of the earliest theories was that someone thought that they were stranded, like whales, and beached themselves at times. But it turns out that they probably died in rather deep water. Mm. This is an illustration showing the evolution of Ichthyosaur. So we can see here the earliest forms. They are quite lizard-like, or look a bit maybe vaguely resembling a crocodile. But over time, we can see here how the body itself becomes more cuneiform, shaped like the body of a tuna or a white shark. And they developed a dorsal fin and a symmetrical tail that enabled them to swim more efficiently through the water. So it's a very nice example of gradual evolution as an animal become adapted to a totally different environment. But no other reptile has managed to transform itself into almost a fish-like shape, like the Ichthyosaurs did. And here we can see what happened. This is the forelimb. If you imagine an ancestral reptile, land-living reptile, we have the bones of the forelimb, the humerus, the radius, and ulna. And you can see all a gradual change. So once you get over here to the most extreme and most advanced form, you can barely recognize the radius and the ulna anymore. And also, interestingly, they lost their thumb quite early, but the later forms added new digits. So some of them might have up to 10, even though their land-living ancestors started off with 5. Another very interesting example of evolution. If we now look a little bit on the record of ichthyosaurs from Australia, the age of the dinosaurs during which the ichthyosaurs existed covers 3 periods. We have the oldest is the Triassic, the Jurassic, which gave name to Jurassic Park, which interestingly includes mostly dinosaurs from the Cretaceous period. And then the youngest period is the Cretaceous period. And during the early part of the Cretaceous period, large parts of Australia were flooded. So we had a large, restricted inland sea covering much of Queensland, and we have plenty of ichthyosaur remains from Queensland dating about 110, maybe 120 million years. In Western Australia, we also had, and that sea was very restricted and not a lot of circulation. So the bottom conditions were quite hostile. but still was a high productivity, so the ichthyosaurs, they liked it there. In Western Australia, about 130, 140, 150 million years ago, Western Australia used to be attached to what's referred to as Greater India. That's the part of India that's now sitting underneath the Himalaya. The Indian continent is being pushed underneath Himalaya. That's why we have that huge mountain range. So if you go back in time, WA was attached to India. And in the earliest part of the Cretaceous, Rift Valley formed. That's how continents split apart. And we can see traces of that Rift Valley, the Darling Fault line to the east. That's part of an old Rift Valley. And as they drifted apart, sediment started accumulating, and we have some of this preserved, for example, north of Kalbarri. And this is showing an image from this area, where we have, in the lower part, there's various sandstones, about 60 meters or 30 meters of sandstones. The basal 15 meters were laid down in rivers. And then as you go up, the upper 15 meters were laid down in close to the shore in a coastal area. This is one of our volunteers. On field trip, we always bring volunteers with us. We very much depend on volunteers. That applies for paleontology worldwide, I'd say, when it comes to field work. And here's one of our best. He's extremely good at finding fossils. So the last time we went up to Kalbarri was in 2008, I believe. We had some of the fossils we found on that exhibition were on display in our Discovery Centre. And at the top of this sandstone unit is what we refer to as a hard ground. It's a fairly hardened rock, maybe about 20 centimeters thick. And it's very rich in fossils. It contains extinct cephalopods, a group called the ammonites, plenty of fossil wood, 120 million year old fossil wood, but also isolated bones and partial skeletons of extinct marine reptiles, including these ichthyosaurs. We also found a tail vertebra, probably of a dinosaur, a carnivorous dinosaur. The only problem with this sediment is that it was laid down basically just maybe a few hundred meters or possibly a kilometer offshore in turbulent water, very well oxygenated. And when an invertebrate animal dies, and it sinks to the bottom eventually, there's a lot of animals that will chew on it. Sea urchins, for example, they will chew on any phosphate, and bones contain a lot of phosphate. So they're really, really well preserved. In order for a fossil to be really well preserved, for example, the Queensland ichthyosaurs, they're much better preserved because the bottoms there were very poor in oxygen. So there was not a lot of scavengers, so they are better preserved. And this is this fossiliferous layer, and this is part of an ammonite weathering out of the rock. And here is our volunteer, and he's actually found this is a backbone, a vertebra of an ichthyosaur. I think we found 8 bones in total, and on this last field was the first time we found a vertebra of a giant pliosaur, which is a different type of extinct marine reptiles. It could grow to enormous size. And here's another vertebra, and the state of preservation is quite typical for these outcrops north of Kalbarri. It's a little bit corroded, probably a lot of scavengers have been chewing on it a bit before it got covered by sediments. But they are well mineralized. Some fossils are extremely fragile. For example, on the Nullarbor plain, you might have heard of the Ice Age megafauna that we are finding in these caves. And these animals, they just died. Well, they fell down into the cave and then they died, and the flesh rotted away, but the bones have never been covered by sediments. So when the collagen fibers are rotting, normally if a bone is buried in sediment, there will be various minerals replacing the organic material. But these nullarbor bones, they haven't been buried by sediment, so they're very, very fragile. But these are extremely well mineralized. There's plenty of groundwater that has been flushed through the sediments over millions of years. As I mentioned, we actually have found a few partial skeletons in these rocks up in Kalberry, and this is a photograph from the Diamonds to Dinosaur gallery. I hope everyone here has been and had a look at. And this is a Plesiosaur. That's another type of extinct marine reptile, and it's a nice skeleton. Well, we're actually cheating a little bit. It's bits and pieces from 3 individuals, but it looks much better. And this is some tail vertebrae of an ichthyosaur that we found in another area. There are 2 main areas, well, there are basically 2 areas where we find ichthyosaur remains in WA. One is just north of Kalberry, and the other one is in the Duralia range, which is about 30 k's east of Coral Bay, in rocks of exactly the same age. So the state of preservation is also very similar sediment, a sandstone. A couple of months ago, I was contacted by a friend of mine, and he said that an amateur collector had found some beautifully preserved ichthyosaur bones in a unit called the Windalia radiolairite, which is the unit that sits on top of these sandstones that yields these ichthyosaurs in Kalberry. And the Windalia radiolairite, you have outcrops of that all the way from Kalberry and all the way almost up towards Exmouth. And these are absolutely beautifully preserved. You can see the state of preservation is much better than those that we are finding in these sandstones in Kalberry. And I had opportunity to examine it for a couple of weeks, but then I had to return it. So demonstrates that there certainly is potential to find not only associated skeletal remains that are not beautifully preserved when it comes to the bone texture, but some rocks actually contain perfectly preserved bone, and hopefully we'll be able to organize a few field trips out there and see if we can find some really perfectly preserved ichthyosaur, including the skull and the whole lot. Certainly there's potential for it. The common ichthyosaur that we find in Australia belongs to a genus called Planetary, and this is a reconstruction here. You can see that it's a very advanced form. It's up to, I think, close to 10 digits and a large number of individual phalanx that makes up the front paddle, and a large eye, and quite a large species, maybe 7 or 8 meters in length. This just to show you the change in diversity in these ichthyosaurs over time. Here it is the age of the dinosaurs. We have the Triassic, the oldest period, Jurassic, and Cretaceous. And you can see when we're down in Triassic, the first ichthyosaur, they are quite abundant with quite a few forms here. As we get into the Jurassic, you get fewer and fewer genera, and once we get into the Cretaceous, just one single genus with a few species. So the ichthyosaurs are clearly on decline. We don't know exactly why. It could be due to competition with plesiosaurs, and once you get up in the Cretaceous, it could be competition with large lamniform sharks. Some of you may have been to my previous talk last year when I talked about these giant sharks. And these are some potential predators of ichthyosaurs. This is a giant pliosaur, Kronosaurus, well known from partial skeletons found in the Greater Teton Basin in Queensland. And we think we found a tail vertebra. It's certainly big enough, and it's not perfectly preserved, but by the look of it, it could well be a Kronosaurus. That was found in 2008. So that's something we really would like to find up in Kalberry, a whole skull of that would be 2 or 3 meters long with teeth the size of bananas. So With a bit of luck, we may find one. I just included this random picture because I like sharks. Sharks is a potential, certainly a plausible competitor for these Cretaceous ichthyosaurs, because we know there were very large lamniform sharks around when the last ichthyosaurs lived in Australia. So it's possible that they did had something to do with the extinction, certainly with the decline. The extinction, I have a better theory about what might have caused the extinction of the ichthyosaurs. We'll get to that in a moment. Oh, this is a seemingly random picture. Anyone who can, well, obviously here we've got someone who's filling up their car with fuel, and these are phytoplankton, like algae. Anyone who, what do you reckon is the connection between filling up your car with petrol and marine algae? Yeah, the source rock of hydrocarbons is basically marine algae that died tens of millions of years ago. So now we can extract this oil and use it as fuel. Oceanic Anoxic event. That sounds almost like a cheerful thing. Oh, I just had a little Oceanic Anoxic event last week. But as we shall see, it's quite the opposite. And there is a strong possibility that one of these Oceanic Anoxic events had something to do with the extinction of not only the ichthyosaurs, but the large pliosaurs. Kronosaurus was one of these pliosaurs, and countless of other animals, especially those living in the deeper parts of the ocean. What a pretty black band. This is from an outcrop of presumably limestone rocks, and you can see it's a bit tilted. Over the millions of years, as mountains are formed and continents move around, layers often get tilted. It's nothing strange at all. But the interesting thing is that this is an old seafloor. And we can see here, so seems to be an alternation between maybe more carbonate-rich sediments, and then we have a bit of a marl. Maybe that's seasonally, at a seasonal change, where you get more input from rivers. You might get them in marl, and then limestone, marl, limestone. Suddenly we get into this really dark black band. And this band dates to about 93 million years ago. And it doesn't matter where we look on the shelves or the shelf sediment of that age, we have this black band everywhere. In England, Australia, doesn't matter where you look, it's everywhere. That has to do with this, what I refer to as an oceanic anoxic event. And let's go through the different stages. Stage 1, CO2 outgassing. I'm sure all of you have heard and read a lot about the concern of governments of the rising CO2 levels in the atmosphere from burning fossil fuel. Talk to your plants. That's a seemingly random comment. Not sure. Have any of you ever heard about that? That's what I was told. If you want your plants to grow, you should talk to them. Anyone heard that? It does work. And the reason it works is that the single most important macronutrient for plants is carbon. And when we exhale, that air that's coming out of our lungs contains 5% CO2. That's an enormous amount of CO2. So if you stand close enough and just breathe on your plant, they will just get a boost of carbon. It's true. People who have a greenhouse and they want to maybe induce flowering, they often inject CO2 into the greenhouse. So talk to your plants, they'll grow much better. Some people who have aquariums, and if they have aquatic plants, they breathe into a bag, plastic bag, and then they sort of squeeze those bubbles into the water for the same reason, to inject CO2 in the water. So the first stage of this particular Oceanic Anoxic event that took place 93 million years ago, there are several, but this one was a severe one. We also had a CO2 outgassing, and I'll just come to that in a moment, where that CO2 came from. We know it's coming from today, we are burning fossil fuel. But also release of micronutrients. That's another thing that plants and algae need. An example of a micronutrient, that's essential nutrients that the plants needs in small amounts, like iron, for example. That's a micronutrient. The crust of the planet is made up of maybe about a dozen plates, what we call tectonic plates. These plates, they move around all the time relative to each other. For example, we are moving towards Indonesia by about 1 millimeter every 3 days. Doesn't sound a lot, but the tens of millions of years, that's quite a bit. So the plates, they move around all the time. We are part of this big plate. We are heading towards Indonesia. You can see here, South America is moving away from Africa. North America is moving away from Europe. During volcanic eruptions, there's a lot of gas being ejected, and one of the gases is CO2. And what happens is that when these plates, in places they pull apart from each other. For example, right in the middle of the Atlantic, see if I had a right here, they pull apart and we get something called the mid-Atlantic ridge. And sometimes that ridge reaches the surface. Iceland, for example, is located right on one of these ridges. So what happens is that you have outgassing of CO2, you can have it underwater, and also if you have plates that pull apart from each other, that means that somewhere they have to dive under each other. Otherwise the whole planet would just get bigger and bigger and bigger, like blowing air into a balloon. And those areas where the plates dive under each other are called subduction zones. And the west coast of South America is a very good example. So what happens is that what we call the oceanic crust dives under the lighter continental crust. And when it does so, it injects water, because this is obviously has a lot of water in it, since it's oceanic crust. And when you inject water into the hot magma, or the mantle that's really hot, it lowers the melting point, so it melts. So you have all these magma rising and you get lots of volcanism. And again, that will outgas a lot of CO2. And during the mid-Cretaceous period, the average velocity of these plates was higher than normal. So they moved around a lot. So we had a lot of CO2 being released by this volcanic activity. And when you have tremendous amount of CO2, let's say we have maybe 3 times or 4 times higher levels of CO2 than we have today, you get into a state of global warming, a greenhouse world. So the temperature will go up, it will go up a lot, and it will go up quite quickly. And one of the effects, the 2 effects that causes sea level rise. I'm sure you all have heard about the government's concerned about the sea levels rising, the Maldive Islands, that will disappear, and our coast will be flooded. And one of the effects global warming has is, of course, that it heats up water, and as the water heats up, it expands. Anything you heat up will expand. And that might account for maybe 30 or 40 meters of sea level rise. And another thing is that when you have, at the mid-oceanic ridges. This new crust is hot, and it takes a long time for it to cool. As it cools, it shrinks in volume. And that takes millions of years as it slowly moves away from the mid-oceanic ridge. And if the plates move around fast, that means there will be a larger volume of this hot crust that pushes up the water onto the continent. So that's another reason why we had a major flooding during 93 million years ago. Those two factors combined. And another effect of higher sea level is we get increased weathering of rocks on land. Why is that? Well, when the sea level rises, you get a more maritime climate worldwide. During sea level fall, you have the opposite effect because you have huge, the continents get bigger, so it takes obviously a longer distance for the clouds to cover to reach the interior. So by the time they get there, they already dropped all the rain. So higher sea level, increased weathering, and the reason more water creates a high degree of weathering on rocks is that the most important component for weathering of rocks on land, like a granite, is carbonic acid. And carbonic acid forms when water gets in contact with CO2, which we have in the atmosphere. So we had increased weathering of rocks on land during this interval. This is another random picture. Anyone has a goldfish pond? No one? You have? What do you reckon would happen if we managed to sort of seal off your whole garden and raise the water level so it was about half a meter higher than the pond? Can you imagine the mess that would create? All the other plants that you've been fertilizing, you have all that soil, it would create an absolute total mess. That's what happened 93 million years ago. We had a very rapid sea level rise. So the continents were flooded, and all that soil was just washed out into the oceans. And we had the volcanic activity, some of it along the mid-oceanic ridges, pouring out a large amount of micronutrients, like iron. So we had an enormous fertilization event, just pouring in fertilizers into the ocean. What do you get if you pour in fertilizers into your pond? You get a algal hell. Yes, so we had massive algal blooms taking place 93 million years ago, because they were all being fed by all these macronutrients, nitrogen, phosphorus, potassium, being washed out due to the sea level rise, and also due to the increased weathering of rocks, granites, etc. And obviously all this fertilizing, that creates, as I said, massive algal blooms. And when these algae died, they fell down to the ocean floor, as they always had. But due to the sheer volume of this organic material, the oxygen could not be replenished. It was just, the whole system was totally overwhelmed. So all oxygen was used up to oxidize this material. So anywhere below 130, maybe 140 meters, there was no oxygen anywhere in the oceans, anywhere. That's why we find these black bands. There's all organic carbon from this big giant fertilization experiment that nature carried out. So, and also when you have an oxygen-free environment, some bacteria, they can tolerate an oxygen-free environment. They use sulfur, and they create hydrogen sulfide, which is very toxic to life. That in combination with the fact there was no oxygen meant that basically anything that lived below 130 and 140 meters or dependent on prey that was living below that level just was wiped out. And we get these black bands formed worldwide. North of Kalbarri, this Cenomanian-Turonian boundary event is actually preserved. This is Cenomanian rocks, and as we get up into about here, you can sort of just see that there actually are laminations. It's not as black as some of the other rocks I just showed, but that's partly because it's been oxidized since, because it's just an exposed cliff section. So obviously all the oxygen has had plenty of time to oxidize this layer that was probably dark originally. But the fact that it is laminated shows that there wouldn't have been a lot of life there. But normally laminations are not preserved in the ocean basins. There are all these organisms burrowing and reworking the sediments. You can't see any laminations. If you have laminations preserved, that means that it was more or less an oxygen-free environment. One of the effects of this Oceanic Anoxic event is that the productivity went up tremendously. So we would have had an enormous amount of fish living in these upper 130, 140 meters. And these are all shark's teeth that come out of this layer north of Kalberry. They occur in enormous abundance. And these are from a particular shark called Echinorinus. Obviously it was a pelagic shark. I don't find any teeth of bottom-dwelling sharks in that particular layer. There are plenty of them below, but once you get in there, there's no bottom-dwelling sharks because there's no oxygen. It's gone. This is just an image showing that type of shark, Echinorinus. So we had this system of total death in the deeper parts of the ocean. Now, can nature repair itself? Yes, it can. Or it certainly it's done that in the past. And I'm just going to talk a little bit about the recovery. We had all this organic material washed out into the oceans, macronutrients, micronutrients. So the algae were growing like mad. But algae, they need, for the photosynthesis, they need carbon. That's the single most important macronutrient for them. Where do they get the carbon from? They get the carbon from carbon dioxide. Carbon dioxide is obviously, there's plenty of it in the atmosphere, and the atmosphere and the water, they reach a certain sort of equilibrium. I think now at sea level, I think sea water would probably contain about 3 parts per million, roughly 2 to 3 parts per million, whereas in the atmosphere it's above 300 now. So when the CO2 level was high in the atmosphere, it would have been higher in the water as well. So these massive algal blooms started to draw out carbon from the atmosphere, draw out the CO2. And since they died, they fell down to the ocean floor. There was no oxygen there, so this carbon started to accumulate. Normally it would have been oxidized and reworked again in the whole system. But now it's just piling up in the bottom. So the carbon was being drawn out, and also the oxygen level would have gone up. We have an increased productivity in these surface layer, all this algae, as part of their photosynthesis, they produce oxygen. So oxygen will start to penetrate deeper. If you increase the oxygen in the air, it will increase in the water as well. So that's how this terrible event came to an end. It corrected itself due to the fact that we now had a sink where the carbon could be stored, the extra carbon that was ejected, most likely by the volcanoes. Now, the bone. These ichthyosaurs, for some time, we've known that they did not survive this Oceanic Anoxic event. They have been found, for example, in Bavaria in Germany, very close to the Cenomanian-Turonian boundary. When I did some field work there in 1995, up in Kalberry, I found this beautifully preserved bone of an ichthyosaur. Right here, just below the Cenomanian-Turonian boundary. So that shows that this is by far the youngest occurrence of ichthyosaurs in Australia. It could actually be the youngest occurrence of ichthyosaur anywhere in the world. We are trying to get a better date on these rocks, but we do know that they weren't very far away time-wise from this Oceanic Anoxic event. This is a more complete paddle from Queensland. You can see where it would fit in roughly here. These are very diagnostic for these advanced ichthyosaurs, the ones you get in the Upper Jurassic and Cretaceous. Obviously not very common because I haven't found a lot of them, but still it's a well-preserved bone. Shows that they were there. Today we are in a period technically referred to as an Ice Age periods. From a geologist's point of view, Ice Ages are defined as a time during the Earth's history where we have ice sheets anywhere at sea level, like Antarctica. That's not the norm, that is unusual. But right now we're in an Ice Age. And one of the reasons we are in an Ice Age, we're in a warm period within an Ice Age, called an interglacial, is that we have Antarctica sitting where it is, right on top of the South Pole. And we have this cold current circulating Antarctica, preventing basically heat exchange. If we hadn't had Antarctica sitting where it is, we would have a more effective transport of heat from the tropics to the poles. So we wouldn't have, most likely wouldn't have an Ice Age. Stop climate change, that's a very, the governments are pushing this hard. And that almost implies that, it does imply that the climate should be stable. This climate should be stable, more or less stable. This shows the temperature and the CO2 levels over the last 400,000 years. Does that look stable to anyone here? What we have is, we have 1 cycle, 2 cycle, 3, 4, we're just about to start on the 5th of Ice Ages, individual Ice Ages. And they all have a very similar pattern. At the end of an Ice Age, and you can see the huge temperature swings here from -9 to 3 above present day temperature, up to 12 degrees difference, which is huge. When we get out of an Ice Age, that happens very quickly, geologically speaking, and then we have a warm period lasting maybe possibly up to 10, 12, possibly 15,000 years. And then there's a slow but steady decline with a few interruptions here for maybe 80,000 years when it gets colder and colder and colder and colder. And right now we are here. And if we manage to stop the CO2 rise within a few thousand years, maybe a few hundred years, we will head down into the next Ice Age. Now that will be interesting. But you don't really see anything about that when you read anything by the governments, the fact that they're trying to preserve a state where we're going to have another Ice Age. There's no question about it. This comes at very regular intervals. So you could argue that we are between a rock and a hard place. We could either have another Oceanic Anoxic event, which we probably will if we continue to increase CO2 levels. There's even been talk about fertilizing the oceans with iron to help these algae draw out the CO2. And obviously they would then all die and accumulate and use up all the oxygen, so we'll have oxygen-free ocean floor again. So either an Oceanic Anoxic event or another Ice Age. Pros and cons. Well, if you have an Ice Age, there will be starvation because you get an exceptionally dry climate. During the last glacial period, for example, all the dunes here that you see if you go from the Darling Fault out to the coast, so you go up and down, up and down, up and down. That's just big, huge sand dunes. So all the vegetation will disappear and the sand dunes will be mobile again. Those with you with the beachfront property will suddenly be 40 k's away from the beach. Poor fishing because there will be less nutrients, because there will be a much drier climate, so there won't be a lot of nutrients being washed out by rivers. Dodging housing markets in Canada and Scandinavia, they will be under 3 kilometers of ice. And polar bears, obviously, they'll be happy again. On the other hand, if we have another oceanic anoxic event, fantastic fishing because the productivity in the surface water will be spectacular if you can make it through all the algal blooms. There'll be so much fish. There obviously, when you heat up the oceans, you get a lot more of cyclonic activity. So if you can just make it between a couple of cyclones, you'll do really well if you're into fishing. No more deserts. There will be a more maritime climate. During the Cenomanian-Turonian boundary, right now I think about 29% of the surface of the planet is dry land. Back then it was 19, due to the sea level so much higher. So yes, spectacular cyclones year-round. Stinky oceans, they'll be a little bit stinky from the hydrogen sulfide. But if you can just, you know, bear that and you'll do well if you're into fishing. So these are, it sounds like science fiction, but this will come, one or the other. There's no question about it, it's just a matter of when. So some of our future generations, they will experience one of these two extremes.
Will they have pens by that stage?
Well, maybe. And yeah, that was the last slide I had, and there was not too many of you sleeping, so you did quite well. All right.